In this video, we will try to compute the confidence interval for the mean response or the expected response, and the prediction interval for a new observation, a new response. That corresponds to the first one. The first interval corresponds to the green curve here, which represents the uncertainty of the whereabouts of the regression plane. So where would our y value, our response value, actually be according to this plane? Well, that depends on where the plane is, and we have a certain uncertainty related to the position of the plane. And I should say that the point that we're interested in is the pH value 2.3 and the temperature 38. So we'd like to know what is the expected response if we have those two regressor values. Also, we would like to know what is the prediction interval for a new response, for a single new response at these values of pH and temperature. That corresponds to the blue curve here. And the formulas we need to apply are here enclosed in these squares here. And let's do it in Excel. First, I should say that sigma here represents the variance in the y values over here, the yields. If we don't know sigma squared, we'll use the sigma hat squared, which is the estimate of sigma squared, and the estimate is based on the mean square of the errors, that is the residuals. So the vertical distances from the point to the plane here, it's a little hard to see in this drawing, but you know what residuals are. The mean square deviation in these residuals. We'll use that here. This matrix here is the design matrix. Oops. Design matrix. And it's this matrix which the columns of this matrix consist of the first regressor variable and the second regressor variable, pH and temperature, and then it has a column of ones. The xh vector here is the vector which holds the values that we're interested in our case 2.3 and 38, and also a 1 here. And then I think we're ready to go to Excel. So our starting point is just our data here for the two regressors and the response. And the first thing we will do is to insert a column of ones. So we'll just add a lot of ones here so that we now have a design matrix. And in order to compute this variance, we need to take the design matrix, transpose it, and multiply it by itself, and then invert the result. So I'll do that in one operation here. Now, the design matrix is an n by k plus 1, so in our case it's a 20 by 3 matrix. When we transpose it, it's a 3 by 20 matrix, which we then multiply by a 20 by 3 matrix. That results in a 3 by 3 matrix. And when we invert it, it's still a 3 by 3 matrix. So I'll mark the space in which I want the result, and I need to know the dimensions of the result. And as I just said, it's a 3 by 3 matrix. So I mark that area and I start a formula here. And what we want is a product, a matrix product. So I'll use, in Danish that's M product. In English I believe it's M mult, M-M-U-L-T, matrix multiplication. And the product is between the design matrix transposed, so I'll use the transpose command, in Danish transponere, in English transpose. So I'll transpose the design matrix, which starts at A2 and stretches all the way to C21. So I'll type that. A2, C21. See, that's my design matrix. I've transposed it now, and then I multiply it by itself. So that's A2 and C21 again. Right. So now we have this part here, but we need to invert it. So I'll use the M invert. It's called, I'm not sure what it's called in English, maybe in M inverse or M invert. I'll just close a bracket around here. And in order to make Excel compute this, I need to press Control Shift Enter. Not just Enter, but Control Shift Enter. And then I get the matrix here. Maybe I should give it a caption. So this is the transposed design matrix multiplied by itself, then inverted, or whatever you want to write here. That's what we have here. I might even want to circle it. Right, so that's it. That's this part here. Now I need the XH vector as well. So I'll write that here, 1 and 2.3 and 38. That's this vector here. I can encircle it as well, like that. And then I'm ready to compute, well, what we will find first is the confidence interval for the mean response. And to do that, I need, you can see in the formula, I need the variance of the mean response. So let's write that, variance of mean response. And that's going to be equal to this variance estimate, which I don't have. So before I write the formula, maybe I should find it. The way I find it is to do a multiple linear regression on these data here. We've done that a few times, so I won't drag you through it. I'll just do it in a hurry. Alright, so here we are. We have the regression statistics here, and the figure that we need is the mean square error here. So it's the residual, the mean of the sum of the deviations of the residuals. That's our estimate for the variance in the y values in the yields. So we find the variance of the mean response by multiplying this number here. And let's see what the formula says. That was this one, and then we need the XH here multiplied by this matrix here. So I need an M product, or M mult in English, of this vector here and this matrix here. Right, so that was this part of it, and this matrix here should then, or vector here, should then be multiplied by this vector here. So I'll make a new product here, M product, or M mult, and I should transpose this one. So transpose this matrix here, like that, and close the bracket here. And then I need to press Control Shift Enter to get the result. So that's the variance of the mean response. Then I would like the standard error of the mean response. Well, that's just the square root of the variance. So in Danish, kvadratråd, in English, SQRT, the square root of this number here, that's the standard error. And then we're ready to compute the actual, well, not quite yet. What we need first is then the most probable yield, so that would be the intercept of this point, or you could say the projection of this point onto the plane has this value. We get that by just inserting the regressor values 2.3 and 38 into the model. So that gives us the most probable estimate here. So let's just call it, model prediction, and that's equal to beta naught plus beta 1 times the pH value plus beta 2 times the temperature. So it's really just the function value of the model. So that's 60. And then we can compute the lower bound of the interval. That's just this number, which is the center of the interval, minus, and then we need the t quantile. I think we have the formula here. Yes, t quantile, and let's just do a 95%, and we have n minus k minus 1 degrees of freedom. So I'll write t inverse 0.975. That's the probability because it's a 95% interval, and the degrees of freedom is n, so that's 20 minus 2, the number of regressors, minus 1. So that's t quantile, and then we just multiply it by the standard error of the mean response. So we say multiplied by this number here. So that's the lower bound for the confidence interval. The upper bound is given by almost the same thing. So I'll just take a copy of this formula here and insert it here, and then change the minus to a plus. So what we can say now is that if we did this regression analysis over and over again using new observations each time, this point here, this point of interest here, would intercept the plane somewhere in between 59.66 and 60.58. It would intercept in that interval here 95% of the times. So not always, but almost always. That gives us a confidence interval. But what about, so this was the mean response, but then what about the prediction interval? Trying to predict the value of one single new response. Well, first we need to compute the variance of the new response. And as you may recall here, the variance is almost the same as this formula. Actually, we only need to add sigma squared, sigma hat squared. So I'll take a copy of this thing here into this cell, and then I'll just add sigma hat squared and press Control Shift Enter, and you see that the variance is somewhat larger, actually quite a lot larger than the variance of the mean. The standard error of the new response, single new response, is then the square root of this number here. The model prediction is the same. So I'll just use that number here. And then we can compute the lower bound, and that would be the model prediction minus the t quantile, t inverse, 0.975, 20 minus 2 minus 1, times the standard error of the new response. And the upper bound is given by the same thing. Actually, I'll just take a copy here. Insert here and change minus to plus. So you see the prediction interval is much wider than the confidence interval for the mean response. So 58 and 62. So what we're saying here is that if we conduct this experiment at pH 2.3 and temperature 38, then the outcome, the yield, the response, generally speaking, will be somewhere in between 58 and 62. With 95% confidence. So if we did it 100 times, 95% of the times, this interval would include the true response. Yeah, and that goes to show that it's harder to predict a single observation than it is to predict the mean of a lot of observations.